Chapter 9 video podcast for field methods in hydrology on the topic of discharge measurement. To me, going from velocity measurement to discharge measurement is the natural sequence because in many cases you're going to use velocity data on the way to computing discharge. There are many other uses of velocity just in terms of trying to understand sediment transport and physical habitat for aquatic organisms, but really predominantly velocity is being measured for discharge, and so the technology has been designed with that orientation in mind. Why do we want to know discharge? Well, besides just the basic water balance for the hydrological cycle at the watershed scale, and for validating hydrological models at various points in a watershed, it turns out that discharge is a master variable controlling a lot of abiotic-biotic relations that take place in streams. Here you can see a photo that shows massive gullying at a project where they were changing the channel, and you can see that there's this bank scalloping, bank collapses taking place. Well, knowing the discharge history here and then going from discharge to process of sediment transport is going to be really important. Let's just look at a very few select basic concepts about discharge. When we talk about discharge, we're talking about something related to a mass balance most of the time. It can also come into play in momentum conservation too, but usually in mass conservation. Discharge is given the symbol Q, and I don't think I've ever seen it given any other value. I would imagine that's the case because D is already taken by depth and particle size. So discharge is the rate at which the volume of water moving in a river passes a given channel cross-section. It's given in units of volume per time. There are related values like specific discharge, which would be the discharge per unit width. So if you have a 100-meter wide channel, it might be per unit of 1 meter of width of that channel is another example. I just want to remind you of the basics of mass conservation, that for a channel we can look at how discharge changes in time as a function of its change in storage, where this funny symbol is like V for volume. So the change in a volume, so the volume is shrinking or expanding through time, and that's integrated over that volume. And then also the influxes and outflux, so what's coming in and what's going out. Those fluxes occur over the cross-sectional area of the inlet and the outlet. And here U is taken as that cross-sectional area velocity. When there's no transient storage in the system, then the system will simplify to just, we're getting rid of T here, and just the discharge equals what's coming in minus what's going out. Okay, so how does this apply? Well, it's really important that many times in rivers, flows are fairly steady. That is to say, they don't change much or at all in time. In general, discharge is a slowly varying property of hydrology. There are, of course, examples of flash floods and very extreme events, but for very normal conditions or slowly developing conditions, especially with a slow falling limb, which tends to be more gradual than a rising limb of a storm, then you're going to see what we call steady flow. So discharge does not change through time. As a result of that, that has a spatial effect in that the discharge at any one cross-section will be the same as the discharge at any other cross-section. So Q0 equals Q1, Q2, and Q3. Of course, if you have another source of water that comes in, then that will change over our overall discharge. So discharge is not a function of local shape, and instead that input is affected on by the shape in terms of changing the depths, velocities, and widths that are present at those cross-sections. Another important concept along with steady flow is the idea of uniform channel and uniform flow. Uniform flow is flow in which the shape of the channel is not causing the flow to accelerate or decelerate as the water moves downstream. For example, if you had a constriction that was coming together like the nozzle of a hose, then water would be converging and expanding. And that kind of is illustrated here by these photo above. This is a non-uniform channel because water is expanding, super expanding, converging, and so on. So that's going to mean that there's going to be changes in the velocities, depths, and widths in the river, although the overall discharge is the same. Usually a uniform channel is going to have any arbitrary cross-section, but as you move in the downstream direction, it will remain the same. And so here it's a trapezoidal channel, but uniform doesn't mean that the channel has to have a particular shape like rectangular or trapezoidal. It just means the shape doesn't change. On the right is a view looking upstream in a real non-uniform channel where you can see maybe there's like an island and there's a lot of bumps in here, and then the flow comes into a deep hole and then gets funneled into a narrower run or something. Okay, so we want to measure discharge. It's one of the most important basic elements of the water balance in hydrology. There are many different ways to do it. Some are very direct, like just get out there and measure it, one way or another. And I'm going to show you two overall ways to do that. And the other thing then, it would be to calculate it based on understanding how water flows in rivers. Okay, the first approach is the go out and measure it kind of thing, and there's two broad ways to do that. One is to build a structure of some kind that makes the flow very simple, like make it uniform and highly predictable on the basis of an equation, and then get the things you have to measure in that scenario. The other overall approach is going to be to measure velocity across the channel and compute discharge from that. So with the structures, there's two main structures, weirs and flumes. The concept of a weir is to build a structure that's going to force the flow into a much smaller space, whether you're building a vertical barrier that it's going to flow over, or whether you're making a wedge shape or something like that. But you're basically going into an opening of a known size and shape, and so the discharge is very easy to compute for that shape. And usually the discharge is a function of the height of the water just upstream of the weir, so that also helps to simplify it. The advantages of a weir is that it's the highest accuracy method that's available. You're typically talking about having accuracy of 0.5 to 2% error, so that's really high. The disadvantage is in order to build something into the river, it either has to be a pretty small river or the need for measuring that in a large river is so great that you're willing to do it. However, building a weir into a river can be very dangerous. Many weirs and rivers are deadly. People see them and think, gee, there's a little rapid, I'll just go right through that. And then they get sucked in and killed. And so there's a lot of problems with the use of weirs. There are deaths associated with that, and so that's obviously a disadvantage to the approach. A common type of weir that you see is a sharp-crested V-notch weir. So the sharp-crested means if you look in cross-section, you just see like a single vertical board or metal, piece of sheet metal, something like that. And then cut out of that is a V-shaped notch with a 90-degree angle to it. So it's a right angle. If you look at it, you tilt your head to the side, you'll see there's a right angle there. And so the water is funneled into that and pours through that spout. There's a gauging house associated with it. You may dig out a stilling basin that can collect sediment and just take the flow and even it out a little bit before it goes in there. You can see that in terms of the technology, if we look at it in cross-section, what we're interested in is knowing the height of the water level above the base of the V. And that's designated here by little h. In order to do that, what happens is that we have some pipes that go from the stilling basin into a well that's where the gauge house is. And usually the well could be like a corrugated metal piping or something like that that holds the big hole open. And this shows two pipes that allows the water to equilibrate through these openings so that it's the same water level. What we're doing here is we're moving the measurement out of the channel that could be, a lot of violent flow or something like that, into a very safe, secure, off-channel stilling well. And this shows the classic method with this pulley-based float. So there's a float here, it goes, it's counterbalanced by a weight, and then that spins a wheel. And as that wheel spins, that actually would make a little pen move. Like if you think of a seismograph or something like that, the pen's moving, tracing the arc of the hydrograph on that basis. Now today, we don't use that as much. Sometimes you'll see some form of pressure measurement, and we'll talk about that when we talk about depth measurement, so I wouldn't worry about that right now. One way or another, you need to measure this height, and the relationship between height and discharge is given by a very simple equation. Q, discharge, equals C, which is a constant, times the height of the water above that notch to the 5 seconds power. Now, given this simple relationship, you can see a lot of the action is happening here in C. So what is this constant? Well, engineers have put a huge amount of time into trying to understand that. And over the years, I've read quite a few articles that look into that. I'm showing you here an equation with a huge number of significant digits, and I can't say that that level of precision is all accurate. However, what I can tell you is there's good reasons why engineers want this to be highly accurate. If you have a river and you're diverting water from a river into an irrigation canal to then distribute to users downstream, you can imagine that you want to be diverting the correct amount of water to balance both environmental uses and and societal uses of that water. Well, I've already told you that the error is 0.5 to 2%. That doesn't sound like a lot when you think about it from a scientific perspective. In fact, that's nothing at all. But from a management perspective, from a human perspective, it's a lot of water. Just think about it for a moment. For example, in the 2014 drought in California, water users had their allocations cut 90%. So their entire allocation was 10% of what it was supposed to be. Well, in that context, if you only could measure accurately 2% of the total amount, that would be a problem, because that would mean that 1/5 of water users who remain wouldn't be getting their allocation at all. Now, of course, once you allocate that and you have that floating down the river, again, diverting water and being off by 2% would have dramatic consequences. It means some people might get no water, or overall more water is being taken. And of course, it definitely means that they have to put more water into the river than they need for environmental and societal uses, just to ensure that people are able to take what they need within the precision and accuracy that they can measure what they've taken. So you can calculate C on the basis of the notch angle, and if it's 90 degrees, it has this value of 0.5779. Another type of commonly used weir is a broad-crested rectangular weir. If you look in cross-section, it's nothing more than a block filling the river, and what happens is when the water hits this block, it all has to funnel up into this narrow space. And it just turns out, if you study fluid mechanics, that when water is concentrated like that, the water surface doesn't actually bounce up, it gets sucked down. And the water converges as it moves across that broad-crested weir to the brink. And then there's the overflow, and there can be a pool behind that recirculation as well as downstream. Now this laboratory illustration doesn't show a downstream stilling area, but in this real-world agricultural broad-crested weir, you can see just the perfect symmetry of depth that's represented here. The water is flowing down here. If you fell in this, there is no hope. You are done. So that's an example of why this is such a deadly contraption. But anyway, the discharge for a broad crested weir is given by this equation here, where weir length is this length here, the square root of 2g gravitational constant h to the 5 halves. So again, you just need to put a pressure transducer or some kind of depth measurement that's going to be measuring the height of the water above the upstream top of the broad crested weir. Note that if you're going to use a broad crested weir or any other kind of weir, I encourage you to look up the details of this and really just learn like what are the constraints in terms of the lengths that are recommended and other things like that. Okay, the next concept for measurement with a structure is a flume. So here we're not going to back water up, we're just going to take advantage of the simple fluid mechanics associated with flow through a uniform, simple geometry, either a rectangle or and again, there's going to be a relationship between the height of the water and discharge, and I'm not going to show that, but I will be showing you those equations in a few moments. The advantage is that these are high accuracy, not as high as a weir, and they're harder to automate the measurement of. Like again, you need to drill a hole in the side here, have a pipe to a stilling well, and then measure with a pressure transducer that elevation. Again, the same kind of disturbances. You're disturbing the naturally complex environment with a simple structure. On the other hand, it's not as much of a disturbance as a weir because you're not forcing the water to stop and back up behind the structure. You're allowing it to flow freely. Okay, now we want to switch from structure-based methods to direct observations, which is going to require measurement of velocity in some capacity. And this is the same slide as what I showed in the velocity lecture, where you have an acoustic Doppler current profiler. Remember, this is the device that can measure the velocity all through the depth in bins, along there. And that's all user selectable. It depends on the range and resolution needed and so forth. Recall that this is the depth on the y-axis and distance across channel on the x-axis. You can see the velocity structure. Remember, there's the blanking distance at the top of the bottom where no data is collected. However, this software in here is designed to extrapolate into these zones to estimate the velocities there. Another thing I didn't point out last time, but that's very important, is notice that the right bank is cut off. So it doesn't come all the way up until the depth is 0. And especially on this very steep cut bank on the other side, the water depth is 30 feet. And then there's no data for that last piece over there. And so that could be the case if you have a very steep bank on that side. So the software is also designed to estimate, based on some simple measurements that you make in the field, what the area is and the velocities that would be in those missing pieces on the ends. What's so nice about this technology is all you have to do is just move slowly across the channel, and by the time you get to the far side, you're done. It tells you the discharge. It's actually computing it as you go and reporting it to you on the screen. Then you start on the other side and you come back and just go at a nice slow speed. Usually the speed at which you want to move across, ideally, would be 1/5 of the velocity moving in the downstream direction. So if it's 5 foot per second velocity, that means 1 foot across. And you can imagine if it means 1 foot, it would mean moving across at 0.2 feet. That sounds really slow, but on the other hand, being able to have your computation done by the time you get across, I'm pretty sure that's going to be way faster than doing it with the next method I'm going to show you by wading in the river or using a cableway. If you get into shallower flow where the blanking distance at the top is too much of the flow, like 20% or more, then you really start to have problems, and this probably isn't the best technology. I mean, if it's very shallow, then you should be using a different approach. There are a number of companies that sell ADCPs, and if you go onto YouTube, you can find a lot of videos from those companies that instruct you on how to use this in different situations. This just shows this kind of like kickboard approach, but there's all kinds of platforms now, as well as just mounting it into a motorboat. So it's a really well-developed application, and it's becoming the gold standard in discharge measurement today. The traditional approach that was the gold standard is the velocity area method, and this is what we're going to be doing on our field trip that's coming up. What you do is you break the channel up into multiple sections going across the channel. They don't have to be an equal number, but you're going to usually want to have 15 to 30 sections, and how many you have will probably depend on the sensor technology you're using in terms of how much space it needs, the size of the stream that you're using, and the variability in velocity across the channel. The more uniform the velocity is across the channel, then the fewer sections you would need. But it's still recommended to have 15 sections for a natural channel, and actually the gold standard is 30 observations of velocity across the channel. So we're going to divide it into a number of fractional widths, and then you're at locations representative of each interval, you're going to measure the depth at that location and the velocity. Then for each little piece here, we're going to calculate width of that piece times velocity times depth. That gives you the fractional discharge in each one of these squares, and then you just sum that up across all of the little squares, which is the summation, and that will give you the total discharge. Now, one thing to think about, and I've only got a few little L1, L2, L3, like 3 little sections here. The important thing to understand is where you measure is not at the edge between two cells. Where you measure is going to be the midpoint between two cells. And so that's an important difference that you need to be mindful of when you're doing the homework assignment. So you're measuring in the midpoint, and the velocity you're measuring is intended to be representative of that little interval. So you're measuring in the middle, you know the width of that interval, you're measuring the velocity and the depth, you sum across all those intervals. The last thing I want to tell you is that for the left and right bank, we're usually not going to treat that as a square, because you can see how much of the square is cut off. Like this is a very small channel. Both L1 and L3 are fairly truncated on the side, whereas L2 is pretty rectangular. Well, if you have 30 measurements, the far left and far right one are probably going to be represented by a triangle, not a rectangle. And these concepts, again, they're just so hard, like for me to just talk at you and for you to understand it. The understanding will come when you work on the homework, and then you can play this again and reflect on it while you're doing those computations. So I would suggest that when you're ready to compute this based on the field data you collect, then you come back here and just watch 1 or 2 slides here again. The velocity area method is typically accurate to within 5 to 10%. So remember, relative to everything I just said about the Weirs and Flumes, 5 to 10%, not so good. Also remember, well, I haven't even said this, but in case you don't know, if there's sediment, then water is also going to be moving through the bed. And the coarser the sediment, the more that could be. So that's a huge source of error. So you've got sensor error. You've got the error of taking a continuous function and discretizing it, and then doing averaging depth. Essentially depth averaging, velocity averaging, averaging velocity in space and time as a function of the sensor. So there's a lot of sources of errors that all accumulate, as well as just the water mist going under the channel. The last thing, and this is just what gets my bee in a bonnet, is just it's so much time. I mean, it takes a lot of work to measure a cross-section, and you'll have the joy of that, and you only have to do it once. But it's a result of this that being what we call a hydrographer is a full-time job. Like if you're a dam operator or an irrigator, or the federal, you're a government agency or a power company, you need a full-time person or 2 or 3 whose entire job is to just go around the rivers in your region and use the velocity area and measure discharge. That's a huge expense. And of course, once you've built somebody up with that expertise, you're going to stick with them. So you're talking about a lifelong person, lifelong, health and pension benefits. So it's a lot of cost. And that's why being able to switch to something like ADCP is going to be a dramatically better outcome because, of course, you don't need quite as much overall understanding of rivers if you have this technology at your hand. And so maybe you can do it a little, for less costly person and a less total person hours. And someone can be just very specialized in the use of this tool. Okay, now I need to switch gears. I know this is going to be a little bit disappointing, but the next method that's commonly used, it's so commonly used that I cannot avoid a little bit of math. I have to give you a little bit of math refresher here, and we're going to have to work through some equations that is going to be a little bit uncomfortable, but hopefully with your background in, we're not going to use calculus, but just again, your algebraic background and experience, and if you've taken physics or fluid mechanics, it's all going to help. So we'll begin with some basic trigonometry. Imagine a river that is sloped and that the line of this hypotenuse is that riverbed. Doesn't look like it, but that's the riverbed. Okay, for your convenience, I've just drawn the horizontal line and the vertical line that represents the overall slope of this river. So what we have here then is water that's on top of this slope. And imagine a cube of water. That cube has weight and it's pulled by gravity towards the center of the earth. That weight is not perpendicular to the river, but just straight down. Because water is deformable, then that weight will deform and flow as rivers do, and it is that force of gravity with the deformable medium that causes water to move downhill at a certain discharge. So we can take that weight of water and break it up into two components. A component that's moving down the river called F, and is shown here with a black arrow, and then a component that is normal. And I have a little bit of a notation problem here. This should not say W equals normal to flow, because W is straight down in blue. What this should just say is just there is a component normal to the flow. Let's call it N. Sorry for that typo. We're not so interested in the component that's normal to flow. We're totally interested in the flow that's moving down the river. So if you know the weight of water, then what we're going to have to do is we're going to have to find from the weight just the component that's moving with this vector F. So to do that, we have to take advantage of the slope. So with this diagram, I've got this angle theta, and theta by definition, I can say the tangent of theta equals the opposite over adjacent, dy dx, and dy dx by definition is slope. So I've got the slope, and I'm going to use S here for that, equal tan theta equals dy dx. Note that if I take that same right triangle and I just rotate it around on this point here, what you'll see is that with the same conditions, the sine of theta equals F, adjacent over hypotenuse, which is F over W. So sine theta equals F over W. Now, if you look at sine and tangent functions, you'll see that they almost perfectly overlap, at least as far as the eye goes, between like 0 and 10 degrees. And so as a result of that, it doesn't really matter whether you use sine or tan for most rivers, which are sloped at significantly less than 10 degrees. If you're driving in a truck, up or down a mountain, and you see those signs that say, like turn off here if you're going to like crash, that's usually a 6%, a much steeper degrees. I don't have the conversion between percent, degrees, and all that in my fingertips, but anyway, that tends to be a relatively steep angle, and we're substantially lower than that. However, if you are doing computations for steep rivers, all this doesn't apply, and people tend to use it anyway. So that's why I'm taking the time to just remind you that for low slope, sine and tangent are equivalent, and most things will use sine as a result. Okay, so we're going to look at the balance of forces that represent, and I promise you that we're going to use this to get discharge. It is the most commonly used approach to get discharge, especially when one doesn't go out in the field, but often used in conjunction with field data. So the balance of forces is going to be the weight of water, which is driving flow, and then that's offset by the friction that takes place at the boundary between the water and the bed around it. And that is represented by what we call shear stress. So the weight of water is the unit weight, like any little cube unit weight, times sine theta, recognizing that we take that unit weight and we're only interested in the downstream component. So F equals the weight times sine theta. Okay, and then so if I take that unit weight and I multiply it by the cross-sectional area of the channel times the length of a reach of a river, then that's a volume. Area times length marks out the volume of this domain that you see in this three-dimensional view. So LA is the volume of the river in a reach that's wet, and then we multiply that by the weight of the water that's moving down the river. That weight is being offset by friction, which is governed by a variable called shear stress, given the symbol, the Greek symbol tau with a subscript b for shear stress on the bed. So that shear stress is applied all along the perimeter. So we're going to multiply it times the perimeter and also times the length, because it's not in the flow, but at the boundary between water and the bed, and that's along the perimeter, all along the reach. So that's the balance of forces. You now see that there's L on both sides, so I can cancel that out. And if I move P over to this side, I get A over P. A over P, you may recall from the velocity lecture, is the hydraulic radius R. Also, we're going to assume that sine theta equals the slope. It doesn't, but again, within like 10 degrees, it does. So we're going to use sine theta to represent the slope, and then we also have the unit weight of water. So this tells us that the shear stress on the bed is equal to gamma RS. This is one of the most simple and basic functions that's used in river science for decades. Okay, this is called the depth-slope product. And the reason for that is because R is hydraulic radius, but for many rivers, they're much wider than they are deep. And you may recall from the velocity lecture, the concepts lecture, that in those conditions, hydraulic radius is almost equivalent to depth. So it's called often the depth-slope product. But this is telling us the overall friction that is taking place in the entire reach for steady uniform flow. Now, I've got to pull something out of a hat. You don't have this hat maybe, but it's there inside this hat. Okay, if you've taken fluid mechanics, you know this hat. But it turns out that there's another way to predict the shear stress, and it is using the drag force law. Shear stress is force per unit area. So if I know what is the force of the friction on the bed, and I divide it by the area of the bed, I can get shear stress. This is the shear stress at a point in the river, and it's given by this equation here. C1 is a constant, rho is the density of water, and U is velocity. So the shear stress at a point is proportional to velocity squared. This is depth average velocity, I should say, depth and time. And we can now set these two equal to each other if we assume that the shear stress at a point is equivalent to the shear stress of the overall reach, which is what you would expect if you have steady, uniform flow. So this will lead to the two primary equations that are used for predicting discharge or velocity in a river when you have some data, but you're not directly observing it at the time that it's happening. So first, I'm going to set those two equations equal to each other. Now, gamma is a number. If you refer back to the very beginning of the velocity lecture, I gave you a whole bunch of just properties of water. Gamma is one of them. Rho is a property of water, and C1 is just going to be some number, some constant. So if I say gamma divided by C1 rho, I put that all together, and take the square root of it to take the square root of both sides so I can get U isolated. The square root of gamma divided by C1 rho, we're just going to call that C2. Right, let's not worry about what the number is. We'll just call it C2. And then R and S are our variables, and we're going to take the square root of those. So we have RS to the 1/2. This equation is very important. It's called Chezy's equation. It's the predominant equation used in Europe for estimating discharge. How do you get to discharge? Well, remember from mass conservation, the discharge in water is equal to the velocity times the cross-sectional area. So you put those two together and you just multiply this equation by A and you have a discharge. Already, I bet some of you are starting to drown because we've got a lot of equations that have gone on here. We've looked at the trigonometry of what's happening. We've looked at a balance of forces. And now we've gotten to a relationship that tells us how to predict discharge. So you see, we did get somewhere. And it's worthwhile if you need to just pause, rewind, take a deep breath, and play that a couple of times through. Now it turns out that even though this is mathematically correct, many people made observations and noted that R to the 1/2 wasn't working very well in real rivers. Again, real rivers aren't steady, uniform flows in ideal conditions, and they also have a lot of roughness, right? So as a result of that, they raised R to the 2/3 and got a little bit different answer. And notice here that instead of having just a single constant, that now we have a constant that's alpha, which is just a metric to English conversion value, and an n. Now, let's look at the functionality here for a second. If C was higher in one river than another, velocity is higher. If C is lower, velocity is lower. What this means is that C is something that makes a river move faster, that's not slope and not depth and not width or area, something else. Well, the missing thing that's there is roughness or smoothness. If I have to push water over a very rough surface, then, as you're going to see in some photos in a moment, it slows it down. So in this case, C, because as it increases, the velocity increases, it's a smoothness factor. With Manning's equation, it's 1 over n, and so as n gets bigger, velocity goes down, which means n is a roughness factor. And I can actually convert easily between C and n by just setting these two equations together, work through the algebra, and you'll find that Chezy's C equals R to the 1/6 divided by n. So they're inversely related, and n is a roughness effect. Now, for whatever reason, in the United States, we use Manning's equation quite a lot, and in Europe, they use Chezy's equation. Chezy's equation, if you actually follow through the units of this whole thing, is correct mathematically. Manning's equation is an empirical equation. Its units do not work out, and if you wanted to make them work out, n would have some bizarre units. But they don't have to work out because it's an empirical equation. It's thought to be an improvement over the analytical purity of Chezy's equation. So how do you figure out what value to use with n? Well, for those of you who took my HYD 143 class already, if you dig back into your brains or go back and watch a video podcast, we've seen this little beast before. We used it when you were doing your hydrological modeling, and we had to figure out how fast water was moving down the rivers, which is what we're trying to do now. And you had the opportunity, I think I gave you a value of, 0.07 for grassy surfaces and 0.04 for the river. But it's a value that is somewhat expert based. Roughness is a function of many things. It's the local roughness on the bed due to the grains. It's the presence of vegetation. It could be bar forms like sandbars or gravel bars, islands. It could be that the river suddenly takes a sharp bend, and in going around there's frictional losses or expansion or constriction losses. There's many things that go into it. In a very simple case where it's only due to grain roughness, then we use Strickler's equation, which is n equals 1 over 21 times the median grain size of the bed material raised to the 1/6 power. Now, in my experience, Strickler's equation is really an underestimate. I mean, it's just very rare that grain size is the only factor. Even if you have a rectangular concrete channel, the rectangle alone creates weird effects between bank and bed roughness. So there can be already extra factors that are there. However, Strickler's equation is commonly used for simple geometry channels where there's just a very simple roughness to what's on that boundary. Another way that's commonly used is to start with a base value, like, okay, this is a sand-bedded channel. So I'm going to use my base value for n, 0.02, and then I'm going to add additional values for things that I see in the river, like, oh, well, there's vegetation, so let's add this value, and oh, I have a meander bend, or I have some bars. And I'm going to give you a handout that shows what this particular expert-based approach is. So look for that handout, and you can see what that's involved. Another thing is the USGS reference photo set. This is a website, and I've given you the URL as it exists, but I would imagine that's going to change. So you could always just go into an internet search tool and type in, United States Geological Survey Manning's End photos, and just show you the website that as it exists right now. What they did is they just went to relatively uniform channels. They measured everything and then back calculated an end value. And so there are a variety of photos that are on here for different sites. And if you click on one of these, I'll just pick one arbitrarily and hope that the internet goes, then it will bring up a lot more of the specific information about here we go, of what's here. So it's got the site description, reach properties, a sketch, cross-section, and site photos. And you can see, like, the date of this from 1955, for example. So it gives you all of that information. And then here's an example, just pulling out of that, just a variety of channels. And I tend to be interested in a little bit coarser rivers, so maybe I'm skewed a little bit that way. But 0.03, 0.043, 0.06, 0.075. This gives you a sense of what these would look like. And notice that these examples are all fairly straight rivers. They are very rough potentially, but they're relatively uniform in how they are. But of course, like when you get to 0.075, I mean, nothing's really uniform at the fluid mechanics scale anymore. But in any case, this gives you a feel for that. So another thing you can do is you can back calculate, like I said. So like if I go out and I measure the velocity, I measure the depth, and I measure the slope, I can solve for n, and then I have it. Another thing you can do is you can use a far more sophisticated modeling tool, and I teach this like in my eco-hydraulics class, where you could run a 1D, 2D, or 3D model that has Manning's N in it, and adjust Manning's N to match field observations as best as you can. Well, you can see that if you want to use Manning's equation or Chezy's equation to get discharge, not only do you need to estimate the roughness or smoothness, you also have to get the depth measurement, but that's easy, and slope. And I have to tell you that slope is very confounding, much more than you would expect it to be. And isn't that turning into a theme of this course, that everything is just way harder to measure? I mean, gosh, I've said precipitation's like miserable, prone with error. I've said velocity is just very time-consuming and painful. And now we've got slope, and of course Manning's N, which who even knows if it's real. And then you've got slope. Well, first of all, natural channels are rarely uniform, so that's a problem. But when you're measuring slope, we're not talking about the local slope. When you look at a spot of the river, we're not talking about what you see there. We're talking about the slope over a long enough section of river that we can reasonably consider that uniform. Can we ever reasonably consider a river uniform? Do you think I have an opinion on that? But nevertheless, people are going to do this. We all have to do this. I have to do this. And indeed, some cases you may be working in a canal or appropriately uniformly sloped river. Usually, you're going to measure over at least 4 consecutive riffle crests if you're in a riffle pool kind of river. So this slide shows how slope measurement works using a device called an auto level. If you go back to the geophysical methods presentation, many of the technologies there could be used to estimate slope. The ones I would recommend would be auto level, total station, or RTK GPS. With the auto level method, and this is in fact something that we will do on a field trip, is you set up a tripod, you set up the auto level all nice and level, like horizontal plane. You go to the first location, upstream or downstream, to wherever you're going to walk, and you make your first measurement. Remember that when you measure from the upstream end, you're going to be measuring your smallest number on the graduated pole. Okay, so let's say that has a value, I mean, it could be anything. It could be a value of 1.25 or whatever, and whatever units you're working in. And everything is going to be relative to that. So here it is, we're at the slope break at the downstream end of the crest, and then we go here, well, to the peak, I guess, of this crest, and the peak of this crest, and the peak of this one. And at each one of these locations, you make a measurement. You could also just make many, many measurements down the river and find these peaks later. It's just a question of time and your expertise. If you can quickly find these locations and see them from a single sighting, then you can just go ahead and take the shots. And so the bed slope is the height difference. So you take your survey reading 1 and survey reading 2 and take the difference between those two. Don't worry about the sign, just the difference. And in this case, it's showing 6.5 feet as that vertical height difference. Then you need to know the length between those two. And so that typically means roll a tape measure out along the length of a river. Or if you're in a straight line, you can use an auto level to measure the distance from where you are to the pole. And then if you can turn 180 degrees and measure the other side, then you can get it if it's a straight line. You know, if you make a turn, no, but if it's in a straight line, you can. And so here we have the vertical height divided by distance gives a slope of 0.016. Okay, well, I've thrown out some numbers, so this is a good time to also remember. We've got Manning's N values that were kind of like 0.01 to 0.08. We've got a slope value here of 0.016. So, what's this all about? Remember, this is kind of an aside, but remember, as a hydrologist, you need to start to get familiar with the typical values of things like slope and discharge and Manning's N or Chesney C. Getting that familiarity is going to help you to do critical thinking to decide whether numbers you compute or see or read, whether those are realistic and meaningful or not. But I digress. So also, you may want to know the water surface slope. The easiest way to get water surface slope is to go to the edge of the river. See if I can go back. Oh, here. So go to the side somewhere, find the place where the water is just meeting the bed. Okay, at that contact, so here would be in this spot on the left. If I go back a little further, it would be right where the tip of this arrow is. Measure the ground elevation at that position, and then do that 4 times at the riffle crest. That's the easiest way. If you're in a river, like walking down the Thalweg or something, and you want to get the bed slope and the water surface slope together, you take your survey reading and you subtract the water depth. That's going to put you down to the tip of the pole. And then do that difference between 2 different locations, then you get it. Now, of course, another thing is instead of just going the overall slope from upstream to downstream as shown in this example calculation, would be to get a whole lot of points, or even these 4 points, and then do a least regression best fit line through that and get the overall slope that way. The whole point of getting Manning's equation or Chesney's equation is not just to compute one discharge, but to be able to create something called a rating curve. You may be familiar with the term rating curve, in which one would use the velocity area method or an ADCP direct measurement or a Flume, and you would make those observations and then fit a best line. And so that's what's shown here is like a best line fit to the data that's a nonlinear fit. However, you can also make a rating curve that's a theoretical curve where you just take your Manning's equation, like this. You apply it with the mass conservation to get Q equals A times all this stuff on the right. And you can basically, for any given slope that you measure at a site and roughness, then you can simply know as a function of the, hydraulic radius and then cross-sectional area what the discharge is. So for a very wide channel, you can just use width times depth to get cross-sectional area, and depth is hydraulic radius. But if it's not very wide, then that means you have to measure the shape of the cross-section, and for each stage you have to compute R and A. And there are software programs that are free on the internet that will do this for you, where you just put in the cross-sectional information and it'll compute it. And one of those I believe is called WinXS Pro. WinXS Pro, like, I don't know, Windows cross-section Pro or something. Anyway, we've used that before in the past, and there are other programs like that that are available. What this allows you to do is create a theoretical rating curve as opposed to a field-observed rating curve. So overall, whether you do it theoretically or you just go out and you measure a rating curve, and I should say that with a measurement method, the reason for doing that is it's very easy to have a pressure transducer or like depth sensor of some kind in a stilling basin on the side of the river, so that you're always measuring change in stage. And then you'd only have to go out, say, 30 times a year and measure discharges at a wide variety of flows, rather than trying to measure discharge all the time. And so this is what makes discharge hard, and I'm not sure I've conveyed this logically as I could have, but when you want to get discharge measurement, for hydrology, we often want to get the hydrograph through time, not just an instantaneous discharge measurement. All these methods here were about getting an instantaneous measurement, velocity area, ADCP, Weirs and stuff. But if you want to get it through time, you got to go through a rating curve. And whether the rating curve is your Weir equation, your Flume equation, or Manning's equation, or a best fit empirical function to the stage discharge observations, then this gives what's called the rating curve method. So in the field, we continuously record stage, usually on a 15-minute interval, and we compute discharge from that. Now, let's say you have a big storm that comes through. It's potentially going to change slope, it's potentially going to change roughness, and it's going to change the non-uniformity of the channel. Unless you have a very uniform channel, it's very likely to change that shape, and so the way flow moves through that could change. And so every time that happens, you have to go out and recreate a new stage discharge rating curve. Because of this, discharge measurement, it's expensive. You have to have, again, full-time hydrographers going out to all the places you want to know discharge, measuring each site 30 times or more a year. And not just at low flows that are easy, but you got to get out there in the floods. And Murphy's Law of Hydrology says floods happen at night. So then what do? You're going to get out there in the middle of the night. So that's when cableways and bridges become very important. Things like that. It's tough. Hydrology is tough. I wish I could tell you it was easy, but it's a lot of work to go out and make these measurements. It's expensive and time-consuming. The last thing I want to point out to you, second last, is the idea of hysteresis. Hysteresis means that the direction of how something, the magnitude of something is a function of where you are in the process. So on the rising limb, you might have one relationship between stage and discharge, and on the falling limb, you might have a different one. Okay, so they're often not the same. That happens for many reasons. First of all, the water surface might be quite sloped because you have a very quick response in terms of the driving discharge are the easily saturated areas near channel heads and in the channel, But then when you're drying out later, not only are you receiving flow and turning off flow from those areas, but you're now receiving flow from the groundwater system, which buffers the rate of decline of flow. So if you've taken 143, you may remember some slides I gave on the variable source area concept. You could go back and look at that. If you don't have it, the important thing to remember is just water in a watershed is coming from different places at different times in the storm, and as a result of that, the relationship between runoff at a point and the stage at that point is going to change. The last thing is just deciding on which method are you going to use. I've tried to give you some idea in the pros and cons about this. If you have a very large river, you're talking ADCP or Manning's equation. Or if you're gonna use a velocity area method, you're gonna be doing it from a boat, but that's where ADCP is just superior. Can you afford to build a Weir or Flume at the scale of the river that you have? If you can, that's going to be very good as long as you can manage the danger associated with that. Operational cost of maintenance and staffing is very important. I've covered that quite a bit. Site accessibility and availability of bridges. Like, if I need to go out and I know I'm going to need to get big flows, if I can use a bridge, great. On the other hand, if my bridge is like I-5 or I-95, like some massive, death trap for walkers, then no, I'm not gonna gauge off a death bridge, Okay, what's the range of flows needed? If you don't need a wide range of flows, then it's easy. But usually, of course, floods occur very rarely, and when they occur, you got to have that data. How stable is the reach, and how simple is it? If you have a choice between measuring at a complex bar feature that changes every 2 or 3 years, or a straightaway that's fairly uniform and hardened, choose the straightaway. You have freedom to pick where you're going to do this. Pick a stable, simple place to the best that you can. Hydraulic conditions, like are there recirculations, eddies, complications to the flow, or is the flow not, what if you have a channel but the flow is like pointed at the bank, so it's not straight down the channel but the flow is moving within that, not such a great place. And then ice can be a factor in terms of how you measure as well, as to what technologies can survive being frozen or not. Okay, so that's a pretty long lecture, I feel like, about discharge. A range of technologies. We do have some math in there, so reflect on that. Of course, we will be going out in the field and practicing it and doing this on the homework assignment with your group, so you'll get some experience with this and get a feel for how everything works.